Hi, everyone. Thanks so much for attending. I'm Kat Massey. I'm the director of the Ambient Air Division here at Apex Instruments. And today's presentation is very special. I'm going to be sharing a third-party laboratory evaluation of our VOC analyzer that's been conducted by AECOM. So this was done at AECOM's laboratory facility earlier this year, and this was using our Omni 2240 microscale gas chromatograph. Now, I'm assuming that most of you all have found your way here because you're uniquely interested in volatile organic compounds, but I'll start off the presentation with just a little bit of background information on VOCs for those who might not be so familiar. Then I'll share a little bit of background information about our microscale gas chromatograph, but I have recorded an overview webinar on this topic before, so I'll direct you back to that if you want some more information about the VOC analyzer. And then most of the presentation is going to be a pretty data-heavy talk. We're going to be reviewing the results of the laboratory evaluation conducted by AECOM. And then at the end of the presentation, we'll have some time for Q&A. So save your questions or drop them or write them down in the chat box as we're going. Okay, so quickly, some background information about volatile organic compounds. Many of you all, again, are probably very familiar, but we understand that the presence of VOCs at or near a manufacturing facility often indicates that there's a leak or perhaps there's lost product. And this could also pose a safety hazard, either due to risk of explosion or because we acknowledge that there's negative health impacts that are correlated with VOCs, whether that's acute short-term exposure that's linked to headaches, nausea, and vomiting, or more chronic long-term exposure from VOCs can lead to cancer, liver, kidney, or central nervous system damage. For the use case of oil refineries, if we're identifying VOCs, we're often using EPA method 325A, which is a fence line monitoring application using passive sampler tubes, where passive sampler tubes are deployed at or around the fence line of a facility. They're set out for 14 days to passively sample ambient air and have an absorbent material that collects VOCs. Then these passive sampler tubes are sent to a laboratory where they're analyzed, and then a report is shared often about 21 days after the initial deployment of these passive sampler tubes. So you don't get very good, or you get no time resolution data as to what has been happening at your site or near your site related to VOC emission events during that time. For folks that are interested in getting better time resolution information related to VOCs, we recommend deploying a system like ours, our portable field deployable microscale gas chromatograph, or VOC analyzer for short. This unit's been designed to be deployed out in the field along the fence line of a petrochemical facility. It connects to a cloud software platform where data can be viewed in near real time, which allows crews to make quick decisions about how to respond to VOC emission events, whether they want to go out and find the leak and repair it, or just log the event, or acknowledge perhaps with the use of the metrology station that the VOC emission event didn't come from their facility at all. Now, this is possible due to our Omni microscale GCs. Here's a picture of the device deployed out in the field. This unit is able to speciate many common VOCs with high sensitivity, often the low parts per billion range. We can acquire results within minutes, and we can vary the sampling time as needed. It operates fully off the grid if desired, with the use of a solar panel and battery backup pack. And then the next two bullet points are quite attractive for many users. There is no carrier gas required. We're using just ambient air as the carrier gas with the system. And we do not require frequent calibration of the device. We are using capacitive detectors in this GC, which do not experience much signal drift, as opposed to photoionization detectors, or PIDs, which often have to be calibrated once or twice a week. The unit is low cost. It costs about $35,000. And because of the no carrier gas and the infrequent calibration, this helps keep costs down, operational costs down as well. And the compact size, it weighs about 16 pounds. It's the size of a little larger than a shoebox, allows it to be very easily to deployed and move around to different sites. I'm going to quickly just share a couple of the functions and features of this product. So here's a picture of the unit on the lower left. The Micro GC is manufactured by Omniscient, which is they're a group that's in San Jose, California. And we, Apex Instruments, are the exclusive distributor for this product line. You'll see on the lower side here is the sample inlet port. Again, we're just using ambient air as the carrier gas. And then I'm going to play a quick video that shows how the analyte interacts with the monolithic Micro GC chip. So the dots represent the analyte. Initially, the sample is pulled across the chip over the detector and the column to the pre-concentration material. This is where selective material interacts with VOCs and pre-concentrates here. And the length of pre-concentration is adjusted by adjusting the sampling time. Then we reverse the flow of the bidirectional pump, heat the pre-concentration material, and that causes the analyte to release, pass through the column and over the capacitive detector to be measured. Here's an example chromatogram generated with our VOC analyzer. And if you're familiar with gas chromatography, you'll notice that this doesn't look like typical gas chromatographs you've seen. There are two different peaks here, and this corresponds to the two different detectors, two different capacitive detectors that are used. Now, similar to regular gas chromatographs, we're using retention time along the x-axis to identify species, and we're using peak height along the y-axis to identify the concentration of a sample. But we also have a third metric that's helpful in identifying VOCs, and that's the peak height ratio between the two different detector peaks. And so this corresponds to the changing capacitance of the first detector over the changing capacitance of the second detector. And this allows us to identify chemical species that have co-eluting times. So we're looking at the peak height ratio of the different compounds and able to bin them or classify them based on the peak height ratio, whether it's benzene, an alkane, different polar, non-polar chemicals. So that gives us an added advantage over typical gas chromatographs. This slide here lists different detectable VOCs. In general, we're detecting aromatics, halogenated hydrocarbons, and alkanes. We have built out a library for some of these VOCs, but we can build out libraries for additional VOCs by request. So please reach out to me if you have a VOC of interest that you'd like help analyzing. Okay, now getting into the meat of this presentation. Switching gears to talk about the AECOM laboratory evaluation results. I want to just first read the disclaimer provided by AECOM. So the test results presented here are intended solely for the purpose of sharing information and do not constitute an endorsement, certification, or approval of any product or service by AECOM. The results are provided as is and reflect the specific conditions under which the testing was conducted. And I'd also just like to really thank sincerely AECOM for their collaboration on this effort and for agreeing to allow us to share these results. First, the laboratory setup that was used. We have a particulate filter that's typically placed on the front end of the sample inlet. It's useful outdoors to prevent debris from entering into the system. The particulate filter is here. For the laboratory test, this particulate filter was removed, and the black polymer tubing of the sample inlet was loosely positioned inside of a swage lock fitting here, and that fitting was connected to tubing, which is where the analyte was. And this configuration was recommended by Omniscient, the manufacturer. Some other notes to keep in mind. A reminder that sampling times can be readily adjusted for the Omni 2240 unit. That's done by interacting with the cloud interface. The relative humidity in the laboratory is assumed to be about 40% unless stated otherwise. The use of ND throughout these slides relates to not detected. There's a couple instances on the slides where an external filter is mentioned. This refers to actually using the particulate matter filter. And then on the different plots that I'll share, the dashed red line indicates plus or minus 30% of the theoretical values. And this is a metric that was identified by AECOM, and it's a typical control limit that they use in their gas chromatography work. And it's just a useful visual reference throughout these slides. And then on the right-hand side here, of course, is a picture of the micro GC board. So I thought you all might be interested in seeing that. Okay, this slide summarizes the different tests that were conducted. So first I'll go through different benzene-only tests that were run. So AECOM was varying the concentration and or sampling time. And just keep in mind that the VOC analyzer's limit of detection as well as maximum measurable concentration are both inversely proportional to the sampling time. The next set of tests will look at test standard mixtures, so custom mixtures of different VOCs. And some of those mixtures were also measured in the presence of higher humidity, both at 70 and 100% humidity. And then the last set of tests I'll share relate to higher concentration sample and following blank and carryover test results. So first looking at those benzene tests. This first slide shows the VOC analyzer measuring close to 5 parts per billion of benzene at a 15-minute sample time. And we're seeing for all 13 of these tests, we're measuring very close to the 5 ppb value. Most of these deviations from 5 ppb occurred during the first test of the day, which is represented by that open square or open circle on the plot. And you can see in the table that there's an occasional trace measurement of toluene or xylene, that these values are below the limit of detection. This next set of test results is for 25 parts per billion of benzene and a 5-minute sampling time. There are 7 tests conducted here, and we observe a trend towards underreporting slightly. So we're seeing values that are towards the lower end of that minus 30% of the theoretical value. Now, typically we recommend running this particular unit, this particular Omniscient model at around 10-minute sampling time or longer. However, we do have a different model altogether that's more accurate for running faster sampling times. So just keep that in mind. It's likely related to the underreporting of these values. And then again, we're seeing some variations in the first measurement of the day and occasional xylene readings, but again, this is below the limit of detection here. In this slide, we're detailing various benzene concentration inputs with a 5-minute sampling time. So we're seeing some slight underreporting for lower concentration samples and slightly overreporting of that 250 parts per billion sample. But overall, we're within or nearly within the plus or minus 30% of the theoretical value range for all of these tests. And then the one blank sample we're seeing immediately after the run is just below the limit of detection. On this next test, we're observing 25 parts per billion of benzene at various sample times. Again, keep in mind that the limit of detection varies with sampling time. In general here, we're seeing the VOC analyzer slightly is underreporting the benzene, but we are within that plus or minus 30% range identified by AECOM. So pretty strong results here for a little higher concentration at various sampling times. And the last of the benzene tests here, we're looking at 5 parts per billion benzene that was measured at various sampling times. That first row of the table where we're seeing not detected for the 10-minute sampling time, that value is right around the limit of detection for a 10-minute sampling time. So it's likely related to not being able to pick anything up on that first one. And then we're seeing some trend in general here on underreporting the values, which I'm assuming again is related to the trace concentration of benzene here. But but a little bit longer sampling time, and you can see the improvement in ability to detect that 5 ppb of benzene. So to quickly re-summarize the results from the benzene tests, the general observations we see here are that the first run of the day for the VOC analyzer was generally less accurate. So that kind of points to wanting to do a warm-up run before taking into account those results. We're also seeing an observed trend towards slightly underreporting values in general. And we're seeing that accuracy improves with increased sampling time, which is not at all a surprise. For the 5 ppb benzene 15-minute sampling time, nearly all of those measurements were within the plus or minus 30% of the theoretical value range. So pretty strong performance at the 15-minute sampling time. We're seeing 25 ppb of benzene, and the 5-minute sampling time, there was some underreporting, but most values were within that plus or minus 30% range. When varying the benzene concentrations and 5-minute sample times, we're seeing most of the values were within the plus or minus 30% range, but we could not measure the 10 ppb at the lower 10-minute value at the lower limit of detection range. And then for the 25 ppb benzene and various sampling times, we're seeing some slight underreporting, but all of the measurements were within the plus or minus 30% theoretical range. And finally, for the 5 ppb of benzene at various sampling times, there was a trend towards underreporting, but accuracy improved as the sampling time increased. Moving on to the next set of tests that evaluated custom VOC mixtures at various humidities. This test evaluated 25 parts per billion diluted from the test standard mixture listed on the right. The chromatography library for our analyzer has benzene, toluene, M, and O-xylene used. But note, there's other compounds from this mixture that are detectable using our analyzer, but the libraries for those compounds have not been built out yet. In the results, we see that the analyzer is able to quite accurately speciate benzene, toluene, and O-xylene from the complex mixture. The standard mixture lists M and P-xylene as a combined item, indicating that the diluted mixture contains approximately 25 ppb of M and P-xylene. And this likely explains why the M-xylene measurement appears to be on the lower end of the plus or minus 30% range of the theoretical values. But this is because there was likely not 25 ppb of M-xylene in the mixture, since it was listed as combined with P-xylene. In this next test evaluated, there's 5 ppb of the same diluted test standard mixture as the previous slide. Here we observe accurate measurements for benzene and toluene. Again, the combined P and M xylene would have been about 5 parts per billion, which means that the measured M xylene here is less than 5 ppb and likely right near the limit of detection for this 15-minute sampling time, which likely indicates why the M xylene result is outside of the plus or minus 30% of the theoretical value. Finally, the O-xylene was generally slightly overreported, excluding run 2. The inconsistencies of these measurements are generally attributed to the low concentrations that they're measured at and the small margin of error that exists when measuring trace concentrations. The test on this slide measured 25 parts per billion of a PAMS audit can at 70% humidity with a 15-minute sampling time. Strong results were obtained here for benzene, toluene, M-xylene, and O-xylene, with nearly all of the values measuring within the plus or minus 30% range of the theoretical values. These results at an increased humidity support that the analyzer can accurately speciate individual VOCs from a complex mixture. This next set of results, we're using a different test audit can listed on the right, which includes pentane, hexane, benzene, and toluene. Again, we have the theoretical ability to be able to detect pentane and hexane, but we haven't built out the libraries for those two compounds yet, so we're just reporting on benzene and toluene in this instance. And note that the sample is humidified by running it from a Suma canister. And here we're seeing results for benzene and toluene within that 30% plus or minus range of the theoretical value, if anything, a slightly underreporting of those. And then this slide, we're seeing the same test audit standard. This time we're looking at 25 parts per billion, again at 70% humidity, and this time with a 15-minute sampling time. And we're seeing quite strong performance with really the only blip coming from that first run of the day. It's a little bit underreporting here. All right, and finally, we're using the same test audit standard here. And this test is run again at 25 parts per billion and again at 15-minute sample time with the humidity adjusted to be 100%. And here we're seeing both benzene and toluene within that threshold range and slightly underreporting compared to the 100%. To summarize the results from the custom VOC mixtures and humidity tests, we saw that benzene and toluene were generally really accurately measured from complex mixtures, and that the analyzer performed quite well under higher humidity conditions, even including 100% humidity. In nearly all of the tests, benzene and toluene measurements fell within the plus or minus 30% range of the theoretical values. We observed that M and O xylene could clearly be measured separately from P xylene or other VOCs, while M xylene was often slightly underreported, again due to its combined listing with the P xylene, and that O xylene had a trend towards being slightly overreported. This last set of tests looks at a high concentration sample followed by a blank runs, so looking at carryover effects for high concentration run. For this particular set of tests, 500 parts per billion of a test standard sample can was run. Was run twice, followed by 3 runs of nitrogen-only blanks, and then subsequently multiple runs of air room blanks, so just ambient air from the laboratory blanks. From the table here, you'll see that for the 500 parts per billion run, we're showing in this instance not detected, and at the time that these tests were run earlier this year, the cloud platform and the algorithm had a hard time interpreting higher concentration values in this range. Since then, there's been some algorithm and software improvements to be able to measure and quantify the higher concentration values as well. I wanted to just throw this slide in as well. This is a different test result. This is conducted by Omniscient in their laboratory, the same type of test scenario. So this is flowing 600 parts per billion of benzene, slightly different sampling conditions. They were running 20-minute sampling time, followed by 2 purges of just nitrogen. And they're seeing very similar results where initially the first run after the 600 parts per billion run, they're getting some residual effect and of 12 to 15 parts per billion range, but very quickly they're able to purge the system to get down below the limit of detection. This slide here summarizes the approximate month-long's worth of testing and different blank tests that were conducted throughout that time frame. So in between different tests, blank air of either nitrogen or room air was run, and the results are summarized in this plot. This slide shows all the blank samples that were run at 5-minute sampling time. Note that the 5-minute sampling time, the limit of detection is around 10 parts per billion. So all the values here on this plot, even the one immediately following the 250 parts per billion benzene sample, are below the limit of detection, showing that the analyzer effectively clears out the analyte and doesn't suffer from significant historical effects. Similar to the prior slide, this slide displays a combination of results from blank tests of nitrogen or room air using a 15-minute sampling time. Note there are very few false positive readings here, and most of the values fall below the 2.4 parts per billion limit of detection for this 15-minute sampling time. To summarize all of the tests that were run, we observed very strong quantitative accuracy, which generally improved with longer sampling times. Again, we expected this due to the inversely proportional relationship between limit of detection or maximum concentration and sampling time. We observed that the analyzer handled high humidity tests quite well in the laboratory and wanted to note that this is not to say that the instrument explicitly operates well outside in high humidity, but in the laboratory it did. And we observed that the analyzer speciates gas mixtures very well. There were no observed problems with interfering compounds. Also saw that there was a slight trend towards some false positives in measuring analytes in general recovery runs. Finally, I'd like to thank you all for listening, and please encourage you to ask any questions. Here's my email and LinkedIn if you'd like to follow up offline. Thank you.